Hi everyone, welcome to this tutorial on basic VLSI design. I am Goura and today we are going to break down the delay unit and inverter delay step by step. So let's get it started. The delay unit tau, which is also called time constant, is calculated by the resistance and standard square Cg. In this figure, two transistors are connected. The first transistor acts as a pass transistor, so it shows only a resistors. As the input is connected to gate of second transistor, this transistor will act like a capacitors. So these two transistors can be compressed by this circuit. If we apply a signal like this, the output will be like this after a time unit. The output will get 63% of the input after the delay unit tau. Now for the time constant for a feature size transistor. The time constant will be the resistance for feature size multiplies into the standard square Cg. We have already calculated the resistance for feature size for 5 micrometer technology, that is 10 to the power 4 ohm, and we have also calculated the standard square Cg for 5 micrometer technology of feature size, that is 0.01 picofarad. So the time delay for feature size for 5 micrometer technology is 0.1 nanosecond. Similarly for 2 micrometer technology, the resistance we have already calculated, that is 2 into 10 to the power 4 ohm, and the standard square Cg is 0.0022 picofarad. So the time constant for 2 micrometer technology for feature size, that is 0.064 nanosecond. Similarly for 1.2 micrometer technology, the resistance we have already calculated, that is 2 into 10 to the power 4 ohm, and the standard square Cg that we already calculated, which is 0.0023 picofarad, results the time constant 0.046 nanosecond. On the other hand, time constant is the time taken by the electron to move from the source to drain, and the equation of time constant is given by tau sd is equal to L square by mu n Vds. If you put the standard value of L, mu n and Vds, we get tau sd is equal to 0.13 nanosecond. In previous slide, we calculate the time constant for 5 micrometer technology for feature size, that is 0.1 nanosecond, and here we calculate the time constant, that is 0.13 nanosecond. These are approximately same. Now we want to calculate delays for inverter pair. For NMOS depletion mode inverter pair, both two inverter must be NMOS depletion mode inverter. The ratio of Z pull up to Z pull down should be 4:1. It means the Z value for pull up network is 4 and the Z value for pull down network is 1. In this case, inverter 1 provides 1 tau delay, inverter 2 provides 4 tau delay. Inverter 1 and inverter 2 combinedly provide 5 tau delay. Now we will see how these delays come about. To do this, if we elaborate the inverter pair circuit, it will look like this. As the input is connected to only one transistor gate, we get 1 square Cg gate capacitance. When input is 1, transistor T2 and T3 is on. On the other hand, T1 and T4 is off. Now assume that the delay for inverter 1 is tau 1, the delay for inverter 2 is tau 2. Hence, tau 1 becomes ZRSN multiplied by 1 square Cg. As the transistor 2 is on for inverter 1, the Z value will come from this transistor, that is 1. So tau 1 is 1 RSN multiplied by 1 square Cg, where RSN is the seed resistance for n-channel transistor and square Cg is the standard unit of capacitance. As you know, 1 RSN multiplied by 1 square Cg results 1 tau, so tau 1 becomes 1 tau. For inverter 2, the transistor T3 is on, so the Z value will come from this transistor, that is 4. So tau 2 is 4 RSN multiplied by 1 square Cg. As you know, 1 RSN multiplied by 1 square Cg results 1 tau, so 4 RSN multiplied by 1 square Cg results 4 tau. So tau 2 becomes 4 tau. Hence total time delay tau is tau 1 plus tau 2 results 5 tau. Similarly, we can calculate the total time delay when input is 0. If you want to generalize total time delay, that will be 1 plus Z pull up by Z pull down multiplied by tau. Now we want to calculate delays for CMOS inverter pair. For this, two inverters must be CMOS inverters and the ratio of Z pull up to Z pull down should be 1:1. It means the Z value for pull up network is 1 and the Z value for pull down network is 1. In this case, inverter 1 provides 2 tau delay and inverter 2 provides 5 tau delay. Combinedly they provide 7 tau delay. Now we will see how these delays come about. To do this, if you elaborate the circuit, this will look like this. Note that the gate capacitance is double that of NMOS depletion mode inverter since the input of a CMOS inverter is connected to both transistor gates. When input is 1, transistor T2 and T3 is on. On the other hand, T1 and T4 is off. Now assume that the delay for inverter 1 is tau 1 and the delay for inverter 2 is tau 2. Tau 1 is ZRSN multiplied by 2 square Cg. As the transistor 2 is on for inverter 1, the Z value will come from this transistor, that is 1. So tau 1 is 1 RSN multiplied by 2 square Cg, where RSN is the seed resistance for n-channel transistor and square Cg is the standard unit of capacitance. So tau 1 is 1 RSN multiplied by 2 square Cg results 2 tau. For inverter 2, transistor T3 is on, so the Z value will come from this transistor, that is 1. So tau 2 is Z RSP multiplied by 2 square Cg, where Z is 1, RSP is the seed resistance for p-channel transistor and square Cg is the standard unit of capacitance. As you know that the seed resistance for p-channel transistor is 2.5 times the seed resistance of n-channel transistor. So tau 2 becomes 2.5 RSN multiplied by 2 square Cg. Results 5 tau. Hence total time delay tau is tau 1 plus tau 2 results 7 tau. Similarly, we can calculate total time delay when input is 0.